speaker is a former University of Washington graduate student, UW, got his PhD, and now I have to call him Dr. Michael Tremmel from Yale University. Please join me in welcoming Dr. Tremmel.
Hi, thanks for having me. So, today I'm going to talk about some simulations that we have run that predicts that galaxies like our Milky Way actually have several gigantic, supermassive black holes wandering about that we don't see and maybe will never see, but they exist out in the galaxy, floating around. And so that's what I hope to convince you of in this talk. But first, I'm going to start from the beginning. So when I talk about black holes, there's sort of two types of black holes that we think about. The first one are stellar mass black holes, and these are, I find them to be a bit pedestrian, if I'm honest. Sorry, no offense to those people who study stellar mass black holes, but there's many of them in every galaxy. We know about them for a long time. Every very massive star, which there's lots of them in a galaxy, ends up exploding as a supernova. But the only part that explodes is actually the outside of the star. But the inside, the core of the star, collapses and forms a black hole, which you can't see because you can't see a black hole. But this black hole is about the mass of our sun. So you think about it, these black holes are like if you take all the mass that our sun has and cram it into an infinitely small point, you get a black hole. And they're very cool, if you're into that. But what I like to think about are a bit more exotic than that. Supermassive black holes. These black holes are millions or even billions of times the mass of our sun. So millions or billions of times more massive than those stellar mass black holes. And one of these, we know, exists in the center of our galaxy. And we know that because some very smart people looked at some stars moving around the center of the Milky Way. And they could track the orbits of these stars over about 10 years or more. And they found, okay, these stars are moving about an object that we can't see. And so you can do Kepler's laws, very easy math, and you can see, oh, there must be something very massive and also very, very small at that point in the middle there. Ends up, the only answer that makes any sense is a black hole that's about a few million times the mass of our sun that exists in the center of our own galaxy. And this is pretty crazy to think about, such a behemoth black hole that's pretty close to us, actually. I mean, relatively speaking. But actually, all galaxies, or most galaxies, have one of these supermassive black holes at their center. And in fact, these black holes can do a lot of damage to their galaxy. So when these black holes grow, they can actually fling off a lot of mass into the galaxy. So these are images of two particularly cool galaxies that have a black hole at their center. And that black hole, which is big, but is actually the size of our solar system. So compared to a galaxy, it's very small. But it's causing gigantic outflows of gas that even sometimes dwarf the galaxy itself. You can see in this picture here, these giant outflows. The galaxy is this small thing in the center. So this black hole is disrupting an entire galaxy all on its own, which is really interesting. So there's a lot we want to know about these black holes. How do they affect our galaxies as one, but also where do they come from and how do they get so big? These are clearly not from stars exploding. So where do these black holes come from? Well, as with anything in astronomy, to learn about it, we have to look at it. But as I said, black holes are invisible, so it's hard to see them. But luckily for us, lots of these supermassive black holes, because they exist at the center of their galaxy, have a lot of gas around them. And because they're so massive, they can capture that gas gravitationally and eat it, more or less. That gas falls into the black hole. And as that gas falls into the black hole, it actually gets very hot and very bright. And so even though we can't see the black hole, we can see this gas that's moving around it and being eaten by the black hole. And oftentimes these black holes that get bright, there's a computer-generated one from the movie, oh man, what was the movie called? Interstellar. There we go. Yeah. Really bad movie. Really bad movie. But really great physics. We'll talk. We can talk. Anyway. So these black holes actually can, not only do they fling out all this gas, but they can get so bright. Well, the gas around them can get so bright that they can outshine their entire galaxy as well. So we can actually see these black holes very far away from us, even towards the very beginnings of the universe itself, which is interesting. And we do this using all these telescopes, mostly space-based, like Hubble, Chandra, and, well, sometime soon, JWST. But the problem is that when we look at black holes in this way, we're limited, because in order to see the ones that are far away, we can only see the ones that are extremely bright, and often the ones that are extremely massive. But to understand where they come from and how they got to be so big, we really want to see them at the very earliest times in the universe. And that's really hard because you're only able to see the very rare bright ones, and even that, there's lots of stuff in the way. So when you go all those billions of years back in time between you and the black hole you're seeing, lots of stuff can get in the way and make it hard to see. Oh no. There we go. Okay, so recently you might have heard of gravitational waves in the news. And so far, using LIGO, which actually exists in Washington, one of the LIGO detectors is in Washington State, they observed the merger of two stellar mass black holes. So, okay, that's pretty cool. But what's interesting is, if we say, okay, a lot of galaxies have supermassive black holes at their centers, we also know that galaxies merge sometimes. And this here is showing a simulation of two galaxies that, the simulators basically, they made their galaxies from scratch on a computer, and they flung them together, and they saw what happened. And what they saw is that the central black holes of these galaxies also end up coming together and forming a binary black hole and eventually merging together. And when two supermassive black holes merge, just like stellar mass black holes, they emit gravitational waves. They orbit around each other and create ripples in space-time that we can detect with detectors here on Earth. Now, LIGO won't be able to see these black holes. You can think of gravitational waves like sound. LIGO is sensitive to a certain frequency of sound in space-time, but these black holes are a bit higher pitched frequencies. And so you need something, a bit bigger, actually, to detect it. So what we're planning on doing is launching something called LISA, the Laser Interferometer Space Antenna. And this will be 3 satellites orbiting the sun, not actually orbiting the Earth, but orbiting the sun, connected by lasers that are going to be measuring how space-time is wiggling, how these ripples are passing through these lasers. And it will be able to detect mergers of supermassive black holes all the way back to the very, very earliest stages of the universe, when the universe was only a few million years old. Well, 100 million years old. Okay. But that's really interesting because this is a whole new picture that we'll have, a new window into these supermassive black holes that we had never seen before, which is really exciting. So LISA is going to fly in roughly 15 years or so. So we got some time. But people like me, theorists, are going to kind of predict what sort of things will LISA actually be able to see? How often and where will these black hole mergers take place? And in reality, the simulation I'm showing here is kind of a lie. Galaxies, this happens sometimes. It's a very idealized case. But in real life, in the real universe, this is how galaxies form. Small little galaxies form at early times. This is showing gas in a region of the universe. Small galaxies form at early times, and those small galaxies merge together to form bigger galaxies, and those bigger galaxies merge together to form even bigger galaxies, etc. But it's a lot more messy. There's a lot more mergers taking place, one right after each other. The galaxies are changing with time. Their properties are changing over time. The black holes in those galaxies are changing over time. And so the question is, how many of these mergers of galaxies will result in a black hole merger. Do all of them result in black hole mergers, or only some of them? And what happens to the black holes and those ones that don't merge? So that's what we set out to ask. To do this, during my PhD here in Seattle, I developed a simulation that I call ROMULOS. And what the simulation is, it's a big volume of the universe, a big chunk of the universe that we put in dark matter and gas and all the physics that we want. We run it on a gigantic supercomputer. It took something like, I think 75 million CPU hours to run this simulation. So it ran for several months on hundreds of thousands of computers. And in the simulation, the simulation naturally predicts, like you saw in that video, all this structure, these filaments of gas and dark matter that form, and the galaxies that form in these node points here. So this image here is showing us gas temperature. So these hot regions here are actually dense galaxies forming. Some of them big, some of them small. Here I'm looking at the stars. I'm showing you what the stars of those galaxies look like. They have a variety of colors and shapes. Some of them are all alone, some of them are in big groups. And what we can do in this simulation is we can watch the simulation go through time, and we can pick out events like this. We can pick out where two galaxies are merging together, and we can look at what the black holes are doing during that merger. How are they moving around relative to one another, and how long does it take them to actually merge together in an event that would create gravitational waves? Or maybe they never merge together, and it's actually relatively rare. And this is all purely a prediction of our simulation, which is nice, because we're not putting anything too much by hand. And we can make a prediction for observations from LISA. And what we find, just like those simulations I showed you before, the idealized simulations of individual galaxies, we find that also happens in our simulations. We have a galaxy merger, the points here, the dots represent the black holes. And see, it is possible to have a merger of galaxies that bring together those black holes relatively quickly. Those two black holes merge together to become one, as those galaxies merge and bring them close together. But this actually doesn't happen all the time. We also have cases like this. So in this case, we also have a merger of two galaxies, but the black hole ends up taking billions of years to merge. So this final picture here, the black holes look kind of close, but they're actually going to take another billion years moving around the galaxy before they merge together. And so what's the difference between these two cases is that in this top case here, hopefully, I guess those in the back might have trouble seeing it, both of the black holes have a galaxy around it. This secondary black hole here, you can always see a galaxy around it. The galaxy exists as this dense clump of stars, and those two galaxies interact with each other and bring the black holes together. But on the bottom, this black hole here is all lonely. There's no galaxy around it anymore. It's just by itself, wandering around the galaxy, and it takes a long time for that black hole to find its companion and merge. So we can understand this a little bit better with a movie. So what's happening here is that that small galaxy that brings that other black hole in ends up being destroyed by the bigger galaxy. That small galaxy gets ripped apart by the gravitational force of the bigger galaxy as it interacts, leaving the black hole all on its own. And so this is a more extreme example here. So sorry, the people in the back also might have a hard time seeing this. But there's a small galaxy down here with the white point, that's the black hole. It's small and red, and it's going to fall into this bigger galaxy. This is right from the simulation. And if you watch this black hole, its galaxy right around here is being torn apart. This galaxy that used to be this little puffy nugget around the black hole is being torn apart by the bigger galaxy and destroyed. And it's about to leave this black hole all on its own. So here we see the black hole up here. There we go. And the black hole is going to lose its galaxy, and all by itself, this black hole, this supermassive black hole that's about 1 million times the mass of our sun, is left way outside the galaxy, where it will remain for billions of years and even trillions of years before it ever could possibly make it to the center and find its companion. And so this actually happens quite often, because mergers like this are very common in the universe. Mergers between big, massive galaxies, like those idealized simulations, those are actually relatively rare. And so the result of this is that big galaxies, massive galaxies like ours, that have gone through a lot of these mergers in order to grow as big as they are, actually, we predict, have many of these supermassive black holes. So we already understood that there's a central black hole, supermassive black hole, in most galaxies like our own. But what we're predicting here is that there's actually several other ones that we can't see. We've never seen them before because they exist so far away from the center of the galaxy. So here's a couple images from the simulation of two Milky Way-like galaxies, and the white points and the arrows show the black holes and where their velocities are. And so these black holes are on very wide orbits, randomly strewn about the galaxy. Although actually not quite random, because if you notice, where these black holes are, they tend to, if you look at these side-on images of the galaxy, they don't actually exist in the disk. So galaxies like ours have a disk of gas and stars, and these wandering black holes tend to preferentially exist outside of that disk. And that's because the black holes that would exist in the disk have had shorter timescales to fall to the center. So the ones that stay behind, the ones that have a very long time to reach the center, are the ones that have, based purely on luck from the galaxy mergers, exist outside of this galactic plane. So that's really interesting, but it means that it's a problem to see them, because the disk of the galaxy is where all the gas is. That's the stuff that the black hole can eat to become bright. But these wandering black holes, these million solar mass black holes wandering around the halo of the Milky Way, don't have any gas around them to eat. So they remain invisible to us. And so this is now the next step in the research, is trying to figure out how might we actually be able to get observational proof that these black holes exist. And it's hard, and I don't know the answer right now, but that's where we're at. So the simulations, again, predict that these massive galaxies, through a series of these destructive mergers, end up having several behemoth black holes wandering about on these very wide orbits that still, at least for right now, are invisible to us. Even invisible to gravitational wave observatories like LISA. So not even gravitational waves can help us see these guys for right now. So that's the conclusion. Thanks for listening, and I'll take your questions.